Hello, this is Igor Stenmark at MGI Research. We are at the 2021 Monetized Forum Conference. So at every one of our conferences, we like to bring in outside speakers to share a perspective that may fundamentally alter someone's assumptions, sort of talk about a potential black swan event. One could say that with the pandemic, we all have received our lifetime dose of unlikely events. And yet I think that the next topic about quantum computing, it could be highly relevant to our audience of business, finance, and technology leaders. About late 2019, I went to hear a friend of mine, Jack Hidary, um, do a book tour presentation on his research on quantum computing. The book was called Quantum Computing, an Applied Approach, published by Springer. I already knew going into the session that quantum computing was going to provide a dramatic increase in computing power. What I did not realize was by how much and how this change can potentially alter our lives. Immediately, I wanted obviously Jack come and speak at one of our conferences, but the pandemic got in the way. Finally, now I am happy to welcome Jack Hidary to Monetized Forum 2021. If I was to give Jack a proper introduction, it would take more time than our entire session. Suffice to say is that Jack is a technology industry entrepreneur. He is a visionary. He founded several highly successful companies. He is actively involved in key social issues of the day, and with things like environment, life sciences, social policy, microfinance. So he's really a thought leader, and he's a doer. He gets things done. I have known, in full disclosure, I have known Jack for over 20 years. We would go way back. And the entire time I knew him, he has been always like that. So Jack, welcome to Monetized Forum 2021. We are delighted here to have you as our guest.
Igor, thank you for having me.
It's a pleasure. So to begin, let's start by with some basic definition in simplistic kind of a layman terms. What is quantum computing and why should anyone care?
Very, very simple question. I like it. Good opener. It's an exciting moment now because the vision for quantum computing goes back now to 1979, 1980, when a number of people, Paul Benioff, Richard Feynman, Yuri Manin, and others, had the vision and understanding that one day we could have a new kind of computer. Not just a computer that's faster or better, but a computer that's very different. It actually computes in a very different way. And that, I think, is the first point to make, Igor, when we talk about quantum computing, because I think sometimes in the popular press, you may hear that it's just a faster computer. And while quantum computers can do a few things faster, really it's best to think about it as a wholly different way of getting computation done. So now, fast forward to the last few years, we've seen the beginning of the reality of the vision that was put forward back in 1979, 1980 by these handful of individuals. So it's a very, very exciting time. So getting to your question now, what is a quantum computer? How does it do computing? Well, what a quantum computer is a computational system that takes advantage of a multi-level quantum system to actually do the computation. So let's unpack that for a second if we could. What does that mean? Well, if the fundamental computing unit of a classical computer, and here in our conversation, Igor, let's use classical to mean non-quantum computers.
Binary, basically, yeah.
Yeah, so let's talk about classical computing uses bits, binary digits or bits, and we know about the ones and zeros. Everyone listening to us today will know about ones and zeros. But a qubit, a quantum bit, or qubit for short, is something quite different. Because a qubit, what is it made of? How do you actually make one of these? We can talk about that maybe a little later in our conversation. But a qubit is a multi-level system that is quantum in nature. and can take one of several, in the case of qubit, two different positions, or a superposition of these two positions. And by superposition, let's just think of it in the very easy mathematical sense of a linear combination. If I have one state of 0 and one state of 1, normally in a classical computer, that's my choices. That bit will be 0 or 1. But in a quantum computer, we can actually have what we call a superposition. And without getting into lots of quantum mechanics, let's just think of it as a linear combination. That is, I could put any coefficient number before the 0 element, 0 component of my new state, and any coefficient in front of the 1 state, and put a plus sign or a minus sign and bring these two things together. So I have some amount of the 0 state and some amount of the 1 state, and I have some rules about what exactly kind of coefficients I can put in front of each one, what range of numbers I can put in front of each one. And that really makes this qubit quite special. The other thing to say about quantum computers is that this gives us a very large computational space, much larger than just the 0, 1 of a bit. But also, let's go a little deeper. When I actually put that into superposition, this is real superposition from quantum mechanics. This is not modeling. It's not referring to something that's in superposition. We can do that on a classical computer. This is real superposition. And in fact, if I have two qubits and I create an entangled state between these two qubits, that's real entanglement. So when you're programming a quantum computer and you put two qubits into entanglement, that's real quantum mechanics entanglement. So it's very exciting, actually, in physics today, not only from a computational perspective, but from an experimental physics perspective. We now have a system that we can control better and better every year and actually put these qubits into states of superposition and entanglement. So this is the fundamental difference between a classical and a quantum computer. And this fundamentally different way of computing gives us different capabilities. We will never go away from classical computing. We're moving towards a world that I'm sure we'll talk about today into a hybridized world.
So I just want to make sure that we explain what entanglement means, with dependency, what can be introduced by. Do you want to maybe take a
Sure. So two of the fundamental concepts of quantum mechanics that sometimes throw people for a loop, but now we've come to live with these concepts now. It's been now about 100 years, 100 plus years since the beginnings of quantum mechanics, from the year 1900, Max Planck, to the year 1930, when basically the general understanding of quantum mechanics came together. And superposition, as we mentioned, we could just, for the purpose of this discussion, just think of it as some linear combination of these two states. I have state 0, state 1. I have a linear combination of them. Great. And we can represent these by arrows in a space, vectors in a space. I can have a 0 component and a 1 component, and then that will give me some new vector in the space. A little bit of 0, a little bit of 1 gives me a new vector that represents the state of that qubit. Now let's talk about entanglement. We've known since the early days in quantum mechanics that entanglement is possible. And this, of course, is the very thing that Einstein railed against. He was quite upset, Igor, with the concept of entanglement. He called it spooky action at a distance. And his famous paper, now known as EPR, after the three authors of that paper in 1935, was his attempt to use a concept of entanglement to actually bring down the infrastructure and attack the core fortress of quantum mechanics. Of course, ironically, as often happens in the world of ideas, this very attack, saying that the spooky action at distance must be the logical conclusion of quantum mechanics, now is part of the canon of quantum mechanics.
Right.
So it's a very ironic situation. And had Einstein been with us today, he would be quite shocked to see how much. But entanglement essentially is a sense of correlation across two different objects, let's say, in this case, two different qubits. And perhaps later or another time, we can go into more detail how exactly this correlation is different than correlation we understand in a classical sense.
Cool. So want to share with us, if you can, some benchmarks, classical computing versus quantum computing, a problem. Let's say I want to teach my computer to play chess. How long does it take with a classical machine? How long does it take with a quantum machine?
Yeah. You know, what's interesting is that there are many more things that a quantum computer is not good at than it is good at, right? So when we think about, you know, the kind of things that we're doing today with very robust and powerful classical computers, the wonderful advances in machine learning, in chess playing, in the playing of Go, in all these different advances, this is really much better done, certainly now, on a classical computer. When you have also problems of big data and you have vast amounts of data and you want to do, say, for example, supervised learning, as we say in machine learning, this is really best done today on a classical computer. There are some things, a handful of things, that quantum computers will be quite good at and take advantage of these special properties. So when we think about optimization, when we have problems that have many, many variables and we want to optimize across these variables, classical computers have some difficulty. We have some approximate algorithms that can try to optimize for these scenarios, but quantum computers should give us some new advantages in the area of optimization. Also, in the area of chemistry, combinatorial chemistry, we can think of so many applications of chemistry in our world: drug design, formulating new chemistries for products that we use every day to make sure they're less toxic and more sustainable for the environment. You know, now we're all starting to rethink when we use a shampoo or we use a detergent and it goes down the drain after we use it, where does it go? What happens to it? Well, guess what? It goes into our waterways and ultimately out to rivers and oceans. And current versions of many detergents are deleterious to the environment. And so we can think about reformulating the chemistries. But to reformulate chemistry, we have to speak quantum, because molecules and atoms speak quantum. That's their native language, to use a loose analogy. And so if we want to think about how two molecules will interact, in a way, when we think about two molecules interacting, whether they will bond or not bond, or how they will interact or fit together, this is really, in a way, they're computing with each other. And so speaking the native language of the molecules themselves, because they are interacting at the quantum level, by interacting with the quantum computer that speaks this native language, we can have a clear advantage over today's classical computers. So these are some examples where optimization, be it in chemistry, be it in portfolio management, a number of other different application areas, these will be exciting areas for quantum computers. Now, today, Igor, our quantum computers today across the world are quite early. This is very early days in the building of quantum computers. In fact, there's 7 or 8 different ways that physically you can build a quantum computer, different approaches to build it. You can use photons, you can use trapped ions, you can use superconducting qubits, and there's many more, quite a few more as well. And each one of these has pros and cons. So this is a very exciting experimental moment in the history of computation in general, that human beings are now at the precipice of leveraging the quantum world. And we don't know yet, amongst these various ways of approaches, how all this will shake out. So this is an exciting time.
So what I'm hearing you say is applications are in areas like financial services. I could go and construct a new, filtering or screening mechanism to find great stocks or great investment schemes.
Beyond filtering, you'd probably want to use it for optimization. So let's say you
Optimization.
had a very complex portfolio with thousands of assets in it, and you wanted to optimize for certain goals, be it, in terms of asset preservation or asset growth, or, there's different, as we all know,
Different constraints, basically.
different
Yeah.
constraints, right? So
Yeah.
optimization problems are known to be, they could very easily be combinatorial runaway problems. And in these scenarios,
Exactly. Yeah.
the quantum computers coming up over the next number of years will be, I think, very exciting tools. But again, let's come back to the concept that these will be used in hybridization with the classical
So
computer.
it will be used in conjunction with classical
Yeah.
as an add-on.
Right. So right now, here's the good news about quantum computers. We now have basically standardized across the industry on Python as a primary language to speak to our quantum computers, but we need to speak to them via a classical computer. So the process is we write our Python code, and what's great is so many people know Python, and Python is one of my personal favorite languages. I teach Python on a regular basis to other people who are coders already in other languages, or people who are just joining into coding. I love teaching Python. It's really a wonderful language to start with, but also a very powerful language because of the 130,000 libraries that are now online for Python. And now some of those 130,000 libraries are quantum Python libraries for programming a quantum state. And this is very, very new and very, very fresh and very exciting that these libraries, all open source, made by many companies and academic institutions, are now available online. And so the individual now can go online, can download some sample code, and can import. We know in Python, for example, there's an import statement. You import one of these libraries and you start calling this library. And this library and this Python code will run on a classical computer, typically in the cloud somewhere. And then that classical computer will send messages and instructions to a quantum computer. And those instructions will then be translated into the hardware instantiation of that particular type of quantum computer. So for example, in a superconducting quantum computer, we want to send microwave energy into the area of the actual chip itself in order to affect and apply operators onto the actual qubits. So we think, for example, back to classical computing, where you have ones and zeros, and I can apply a not to the one state and I get a zero state, right? So if I have a transistor in a one state and I apply the not operator to it in a classical computer, on a laptop, whatever it is, I get the zero state. And in a quantum computer, we have our own set of gates or operators. We have the not operator, but we also have operators that we don't have in the classical world. And so in order to make all this happen, we ask the computer to put into effect these operators and gates. And then the Python code goes from the classical computer and then sends messages to controllers in the quantum computer to actually do the microwave pulsing in the example of superconducting qubits. So it's quite exciting to see this hybridization come together.
Yeah, so that sounds like it's going to probably accelerate the timeline for this thing becoming practical, as opposed to just kind of experimental, theoretical, and so on.
Igor, the fact that we now standardize on some language and some frameworks,
that by itself is
this is a very exciting moment now.
Yeah.
And that was already a big step. And that just happened in the last 2.5 years. All this happened in the last 2.5 years.
What do you think is the realistic time frame when most of us will begin to notice kind of a practical impact of quantum computing? I can see how theoretically, yes, there's companies that want to do transportation, complex logistics, supply and distribution chain. It would solve a lot of issues, for example, with transportation. It would solve a lot of issues for life sciences companies doing, things like vaccine discovery and drug research. You could see, lots of other kind of concrete examples. But what is the time frame? What is the distance between now and then we would all kind of in society see impact of quantum computing? Is
Yeah.
it
This is the
weeks, months, years,
this is the
generations?
million dollar question, Igor. I would say that here's how I'd like to frame it, which is drivers, right? You and I, Igor, in our past work together, we always wanted to look at the fundamental drivers that would drive change in a particular industry or field. What are the catalysts? What are the core drivers, as opposed to maybe some peripheral or superficial drivers? And I think there's 3 or 4 drivers. And if we analyze the drivers, maybe we can get a sense of the time frame, or at least we can get a checklist for ourselves so that viewers who are watching our video today and in the coming months can have a kind of a checklist and say, all right, when I see this announcement and that announcement and this announcement, I know that's what Igor and Jack were talking about.
Okay.
I'm seeing some progress. So let me just give some benchmarking and some indicators that I think the audience can use, hopefully productively, as they want to benchmark over the next few years what's going on. So the first thing is we want to look for the fact that this technology is cloud native. And the more we see traction in people launching these computers on the cloud, I think it brings the future closer. Because the cloud, being cloud native by birth, quantum computers as they're birthing are now cloud native. The main way really to access a quantum computer is through the cloud. My personal opinion is that people should not be buying any quantum computers anytime soon. Using the cloud means that you always have the latest up-to-date quantum computer that you can access. And also, of course, you can easily access then your traditional classical computer side by side. So we have CPU, GPU, and QPU, right? And so these different processing units now can all live and coexist in this hybridized cloud format, which makes it easy for me as a developer or a software architect to say, all right, I'll have a bunch of code. I'm going to run this on a CPU. I'm going to run my neural network on a GPU. I'm going to run the quantum code on my QPU and let them all interact with each other and give feedback to each other. So we can almost see the quantum computer as a subroutine from the main code, subroutining out to the QPU, and then coming back with a response saying, hey, I'm finished my part of the job. I'm ready to move on now, right? And so one, I think, thing to look for is the level of cloud accessibility and hybridization with integration with CPU, GPU, and then QPU. So the more that becomes seamless and accessible on the cloud, I think the sooner this future comes. The second thing to look for is not just numbers of qubits. I know people love to focus on the horse race of numbers of qubits. I would caution the audience to say, look at also the fidelity of those qubits. How accurate are they, so that when I put a qubit into a certain state, state 0, state 1, superposition of those two, will it hold? Will it actually stay in that state? Or will it easily knock out of that state due to noise in the system? The systems today, we call them NISQ-based systems, because and the N in NISQ is noisy intermediate scale quantum systems, NISQ for short, coined by John Preskill of Caltech. And these NISQ-based systems, that N is very important, very noisy, as opposed to the laptops that you and I are on right now. These are fault-tolerant computers, right? We have error correction built into these computers that we're using right now, Igor. And that means that, yes, little errors pop up from time to time, but the computer has these checksums that check itself and say, oh, something happened. I'm now going to take a certain algorithm that I have, an error checking algorithm, and I'm going to fix that error and then move on with the calculation. We don't have error correction built in yet to the quantum computers of today. So the third thing that I would advise the audience to look for is advances in the implementation of error correction. And this will then lead to much more robust quantum computers, and therefore the application space will start to really grow in the areas of chemistry, in the areas of also experimental physics, in the sense that we can actually look at different physics happening as instantiated in the quantum computer. And then, of course, other areas such as optimization in logistics, in financial portfolios, and other optimization problems. So I think the future is quite exciting, but it's going to take us years, not months, to get to this future.
So if a company said, look, sounds interesting, I read somewhere recently that, as a computing team somewhere in China that said, look, what we did on a quantum machine in like a few minutes would have taken 2.5 billion years on a conventional machine. How true is that? I have no idea. I mean, you have to tell me. But if a company said, look, we want to do something in this area soon, what should they be doing? Should they be just watching it carefully and waiting for additional indicators as you describe them, kind of major driver indicators? Or is there space for some of the more aggressive adopters of technology to begin to prepare themselves, maybe in financial services, maybe in logistics, maybe in drug discovery, maybe in e-commerce? Like, what do you think companies can and should do, and how should they go about it?
I think it is time for companies to start experimenting with this technology. It's the time to start to gain knowledge. It's the time to start training their engineers and also senior IT leaders in this technology. This is going to be a very impactful technology that we know for sure. Very high impact across many, many sectors of our industry and society. I think it is time for companies to say to a group of engineers, a group of leaders inside the company, we're entrusting you with getting knowledge of this technology, understanding it, going to the conferences, virtual now, but hopefully physical soon in the near term, and also learning how to actually program these computers. And the good news, again, as I mentioned, because we're using some familiar tools, the ramp up is not that bad in terms of learning how to operate this. It's more the mental framework of what does it mean to create an algorithm on a quantum computer. That takes a little more of the training, but the tools are out there. Training courses are out there. There's many good options out there, and it's time to also start doing small experiments. So if you're a pharma company, this is a great time to start running some experiments to understand what would it look like to use a quantum computer hybridized with a classical computer. We can't do anything very, very big and robust yet in that area, but we can start experimenting in that way. And the same for other sectors. So I think that's what I would recommend to companies.
Where should we go for? I mean, obviously nobody wants to buy a quantum computer, but to get access to quantum computing service, where should we go for something like that?
Well, the great news is every day there's great announcements there. There's so many companies now that are offering online access to quantum computers.
Okay.
In the main, it's actually free right now. Certainly to anyone who's a student or academic listening to us today, lots of free access. Even the corporates get some, I think, free access on some of these computers. But every day we're seeing new announcements now online. And we're also seeing, I should mention, Igor, we should talk just a minute about startups. I've been tracking now more than 75 startups
Wow.
that are venture funded in the quantum computing space. And some are focused on the hardware. Some are focused on the control of the hardware. Some are focused on software. And so it's a very exciting moment where the venture funding has begun. It's begun in earnest, Igor. And I think we're going to see a number of these companies over the next 3-4 years be bought by larger companies as people start to really look at the space more carefully. So I think we're laying the groundwork for a really strong ecosystem. And that's what I would also recommend people look at. Don't just look at one aspect of the quantum computing sector. Look at the whole ecosystem. Look at the talent generation out of the PhD programs from many universities around the world. There's great programs all around the world. Look at the ecosystem in terms of venture funding of the startups. Look at the commitment of the large companies in the space. Look at the ability to benchmark one computer with another, and there's more standardization happening right now. And of course, there's so many papers coming out every day that are preprints on archive. It's hard to even keep up with many of these papers, but it's an exciting moment. And I think the next number of years will be really a very robust time where we'll start to see real traction in this space. So we can come back together, Igor, in a bit of time and say, how can we
Let's do
benchmark
it.
the progress since our last talk in this area?
Absolutely. Let's do that.
Great to see you.
Great to see you today. Thank you so much. We're almost out of time. Appreciate you joining us here today. And I hope to see you at the next event here.
Great.
Thank you,
Take
Jack.
care.
Take care.
Bye-bye.